Good morning, students. Welcome to the next topic on this electrostatic potential and capacitance chapter in physics for standard 12. Today we shall discuss the introductory things regarding capacitors. So first thing about capacitors that you need to understand is what it is. What is a capacitor? If you have any two conductors of any shape, suppose this is conductor A and there is another conductor B. So A and B are conductors, and if these two conductors are separated by some insulator or dielectric, in between them there is a dielectric. What is a dielectric? A dielectric is an insulator that can be polarized. Then this particular system is called as capacitor. What you see on the board, this figure is a schematic representation for a capacitor. So how do we define that? A capacitor is a system of two conductors separated by a dielectric. So this definition you can write as the definition for capacitors. So what is a capacitor? Capacitor is a system of two conductors separated by a dielectric. It's not necessary that dielectric be present. Instead of dielectric we can have a vacuum also. That will also do. Then what we do? We connect these two conductors to a battery like so. So what would happen? The battery will supply some charges, and remember this circuit is not complete because this is a dielectric insulator. It does not allow the charges to flow across it. So the positive charges will be piled up on conductor A and the negative charges would pile up on conductor B. Actually what happens? The negatively charged electrons will flow like this. Battery will supply the electrons and those electrons will accumulate on conductor B. They don't have the path to go from B to A. On the other hand, the electrons, the free electrons in conductor A, remember conductors have a large number of free electrons. Those free electrons will move to the positive terminal of the battery. If I draw the path of electrons will move like so. And this process stops within a very small amount of time. Within a fraction of seconds, this process stops. Why does it stop? Because when this electron accumulates here, as I told, it acquires negative charge. Conductor A loses free electrons, it acquires positive charge. These positive and negative charges attract each other. So the positive and negative charges tend to come close to each other like so. Now this being positive, this being negative will create a potential difference and an electric field. Electric field will be in this direction and there will be some potential difference. If the potential difference of the battery be suppose V, then this movement of electrons continue till this potential difference also becomes how much? V. The moment the potential difference between these two conductors become V, so both these potential differences become same. That means conductor A will be at same potential as this positive terminal of the battery and conductor B will be at same potential as the negative terminal of the battery. Since they are at same potential, no flow of electrons will take place. Always remember that charge flows from higher potential to lower potential if it is positive and lower potential to higher potential if it is negative. But if the two potentials are same, charge cannot flow. Then the flow of electrons will stop and we will have a static situation like this. After that, we can disconnect the battery. If you disconnect the battery, we will have a positively charged conductor A and a negatively charged conductor B. There will be some potential difference V, and there is some electric field between the conductors, and there is some dielectric. How the dielectric plays a vital role in the case of capacitance of capacitors, that we will discuss afterwards. So this is the basic meaning of capacitors. In this way, it can store these charges. If these charges are not very high, this can remain as such for a longer period of time. If there is no leakage of charge, then this system can be used to store charge. So capacitors, basically what they do, they store charge. Now here equal and opposite charges develop on the two conductors. Suppose the charge on conductor A is plus Q and the charge on conductor B be minus Q. We say the charge on the capacitor is Q. So we say, remember, the net charge on the capacitor is how much? Plus Q minus Q, that is 0. But we say that the net charge on the, not net charge, the charge on the capacitor is Q. So Q is charge, this is just a terminology, capacitor. So charge on capacitor means one of the plates will have charge plus Q and other plate will have charge minus Q. Suppose V is the potential difference between the plates of the capacitor. V is potential difference between the plates of capacitor, and in between them there is some electric field, that is E. E is electric field between the plates of the capacitor. Now we know that this electric field E is proportional to, the higher is the magnitude of these charges, the more will be the electric field. So E will be proportional to Q. Now we want to relate this Q to V. This electric field is also proportional to V. We know potential difference between the plates of the capacitor, that is V, which you can write as VA minus VB. This is positively charged, so it is at higher potential. This is negatively charged, so we say it is at lower potential. So V potential difference is VA minus VB, and this will become equal to minus integration of E dot dr from B to A. Now if these conductors are large and this space between them is small, then the electric field will be almost uniform in some cases. Clear? In such cases we can say that V is proportional to E. If V is proportional to E and E is proportional to Q, then we can say that this V, potential difference between the plates, and charge on the plates are proportional to each other. So we say Q, the charge on the plates of the capacitor, is directly proportional to the potential difference applied, potential difference between the plates. So this implies Q is equal to some constant times V. That constant we write as C. That constant we write as C, and C is called as capacitance. It is a constant of proportionality and we call it as capacitance. Next we should note that in this relation, when we write Q is equal to CV, we can also write it like so, that Q is equal to, C is equal to Q upon V. This constant C, which we have called as capacitance, that C, you should remember students, it is independent of both Q and V. If we increase V, Q will also increase proportionally such that the ratio Q by V remains same. For example, if you double this V, then V becomes 2V. Automatically Q will become 2Q, such that the ratio becomes 2Q upon 2V, that 2q upon tv is same as q by v, that is c. So c is not going to change by changing v or q. This capacitance has SI unit, you can see coulomb per volt, we can write it like so. This unit is also called as farad. So this is the SI unit for capacitance. Farad, in symbol we write it as capital F. But since it is a large unit, so we use some smaller units like microfarad. So 1 microfarad will be 10 to the power minus 6 farad, and so on. As I discussed, this capacitance does not depend upon Q or V. Are there some factors on which C depends? It comes out to be yes. So capacitance C of a capacitor, it is found to depend, so it depends on this structure of the or the shape and size of this capacitor. So it depends on shape, size, this is separation between the conductors, separation between the conductors. So these are the parameters. So basically capacitance depends upon the shape and size of this system of conductors. Then we have symbol for capacitor. A capacitor is usually represented by a symbol like so. We have two parallel lines. So we denote its capacitance by C like this. So this is the symbol for capacitor. If this capacitor has variable capacitance, then we indicate that by putting an arrow like so. So this is symbol for variable capacitor, and if you don't put the arrow, it will have a fixed value of capacitance. So these were some basic ideas regarding capacitors. They have important functions in circuitries. We will see them in some details. The first topic under capacitors that I would like to discuss today is the parallel plate capacitor. Okay, next we would like to discuss parallel plate capacitor. So as I have discussed, capacitor includes a pair of conductors. You can see students like this. This is an aluminum foil, this is also an aluminum foil. Basically this is what we refer to as parallel plate capacitor. Here the two plates, you can see these two plates are placed parallel to each other and there is some gap between them. This gap, if we minimize, we will find that the capacitance of the capacitor will be large. Here I have taken them in the shape of rectangles, but these plates can be of any shape. They can be triangular, they can be circular, and so on. So such a pair of metals, if we connect to a battery, then as we have discussed earlier, one of them gets positively charged, other one gets negatively charged, and they will have some capacitance. In this topic we would like to discuss what is the value of net capacitance for such a parallel plate capacitor. Here we have represented an schematic representation for a parallel plate capacitor. These two are the plates. They have been connected to a battery, because of which they got charged. So B acquires positive charge, A acquires negative charge. Suppose the charge on these plates be plus Q and minus Q. That is the charge on these two plates. Clearly there will be some electric field in between the plates, and that electric field will be directed from the positive plate to the negative plate, and let that electric field have some value that we write as E. In the region outside the plates, that is in regions 1 and 2, the net electric field will be 0. Reason being, see, this is a plate, conducting plate, and it has, suppose a sigma as a surface charge density, this has a minus sigma as surface charge density. Let A be the area of the plates of the capacitor, As I discussed, this plate can be circular or triangular or square. It will have some area. So A will write as area of the plate of the capacitor. Q and minus Q are the charges on the plates of the capacitor. Sigma be the surface charge density. Then we can write sigma is equal to Q upon A. Likewise, minus sigma will be minus Q upon A. In the region outside the plates, in region 1 for example, here, due to positively charged plate, the electric field will be away from it, and due to negatively charged plate, the electric field will be towards it. And what are their values? Their values are sigma by 2 epsilon naught and sigma by 2 epsilon naught. The values are sigma and sigma. It is minus, so the electric field is directed towards the plate, and it is plus, so it is directed away from the plate. So what will be the net electric field? They will cancel. And from where did we get sigma by 2 epsilon naught? This we have already derived for a plane sheet of charge having surface charge density sigma. The electric field has that value. So E is equal to how much? In region 1 it becomes sigma by 2 epsilon naught minus sigma upon 2 epsilon naught, that is 0. Now let's say in region 2. In region 2, due to negatively charged plate, electric field will be towards it. How much? Sigma by 2 epsilon naught. And due to positive plate, it will be away from it. How much? Sigma upon 2 epsilon naught. Again they will cancel. So in region 1 as well as in region 2, you can write the electric field is 0. So E1 is equal to E2 is equal to how much? 0. So in between the plates of capacitor, the electric field E will be how much? Due to positive plate it is downward, and due to negative plate it is again downward. So both of them are in same direction. So we'll write sigma by 2 epsilon naught plus sigma upon 2 epsilon naught, and therefore electric field will become how much? Sigma upon epsilon naught. So this is the expression for electric field between the plates of the capacitor. Now this sigma is how much? It is Q upon A. So sigma I will replace it by Q upon A. So we have E is equal to this much, Q upon A epsilon naught. Next, the potential difference between the plates of the capacitor. Now B is at higher potential plus, so we write the potential difference between the plates of the capacitor as V plus minus V minus. V plus I can write as VB as per our figure, and V minus we can write as VA. By definition, you know students, this is nothing but minus integration of E dot dr from A to B. This is the definition for potential difference. Now this E is constant. Now I have taken this as x-axis. So or in general it may not be x-axis. So we have started from this point and we are moving in this direction. So this is the direction of R or increasing dr vector. So dr vector will be from A to B as per our convention. But electric field is directed opposite to that. So E dot dr will become minus E into dr into cos 180 degree, because E and dr vectors are in opposite direction as per our figure. A to B. Dr is in the direction from A to B. Cos 180 becomes minus 1. So this minus and this minus becomes plus. E is constant, so E will come out of the integration. Integration dr is nothing but R. From A to B means from this point to that point. So R is the distance, this distance. So from A to B, this distance is how much? R. Clear? Oh sorry, this distance is how much? D. So this R is equal to X is equal to D. So our expression becomes E into D. So potential difference between the plates, we have got V is equal to E into D. Put the value of E is equal to this much. So we get V is equal to Q upon A epsilon naught, and then we have that D. Now we have discussed, students, earlier that if C be the capacitance, then Q is equal to C into V. We have discussed that Q is proportional to V, so Q is equal to C into V, where C is a constant. That constant is called as capacitance. So how much will be that C? So this implies that C will become equal to Q upon V. And if you see this particular expression, Q upon V will become how much? It will become A epsilon naught upon D, and this is what we wished to derive. So this is the formula for capacitance due to a parallel plate capacitor. It is given by the formula A epsilon naught by D. Now see, I have discussed earlier that capacitance depends upon the physical dimensions of the capacitor. See, it depends upon area of the plate. It depends upon the separation between the plates D. And we will find that it also depends upon the medium. Here the medium we have taken as a vacuum. That's why the formula is A epsilon naught by D. We will see afterwards that if this gap between the plates is filled with a dielectric, the formula will change to C is equal to A epsilon naught times K upon D. Next, let us quickly see what would be the effect of inserting a dielectric between the plates of the capacitor. Here we have the parallel plates of a capacitor. The surface charge densities are plus sigma and minus sigma. We have already discussed that the electric field between these two plates will be in this particular direction, and its value will be how much? That we write as suppose E naught. So E naught is equal to sigma upon epsilon naught. We have discussed in the last topic. And its capacitance was given as how much? C is equal to A epsilon naught upon D. These two things we had discussed. Now suppose we insert a dielectric in between the plates, like so. There is no gap, just it completely fills the space between the conductors. Now in dielectrics we have discussed, students, that in presence of external electric field, due to stretching and due to reorientation of dipoles, whether polar or non-polar molecules, on the opposite faces we develop charges, like so. This one will write as suppose, and this electric field will be in opposite direction. So this was our E naught, this E naught, and due to polarization, surface charge densities plus sigma p and minus sigma p develop, and that results in an electric field opposite to the direction of E naught. So this is E in, so net electric field will be in this direction, and that E will be equal how much? E naught minus E in. This is the magnitude, and its direction will be in the direction of E naught. We wish to compute how much will be this particular E. So E we have written E net, the net electric field inside this region will be E naught minus E in, where E naught was how much? Sigma by epsilon naught. So E naught is our sigma upon epsilon naught. E in is how much? Sigma p upon epsilon naught, and they are in opposite direction. So E naught was due to this plus sigma minus sigma, and E in is due to the polarized charge densities, that is sigma p and minus sigma p. This gives us the value of electric field E as how much? We will subtract this to sigma minus sigma p upon epsilon naught. Now this is the net electric field in case of dielectric inserted between the plates of the capacitor. Sigma is the free surface charge density on the plates of the capacitor, and sigma p is the surface charge density that arises due to the polarization in the dielectric. For linear isotropic dielectric, which we have discussed earlier, it is found that this sigma p is proportional to E. Polarization is proportional to E. Actually, we know polarization is proportional to E for linear isotropic dielectrics. Polarization depends upon sigma p, so we write sigma p is proportional to E. I mean E naught. But what is E naught? E naught is sigma upon epsilon naught. That means I can say E naught is proportional to sigma. So this implies sigma p is also proportional to sigma. If this is true, then I can write sigma minus sigma p, that is this E, times epsilon naught. This sigma minus sigma p should also be proportional to sigma. Why? This is sigma, no doubt. This is sigma p. Sigma p is directly proportional to sigma. So therefore, their difference will also be proportional to sigma. And if this be true, then we can write sigma minus sigma p is equal to some constant times sigma. That constant we write as 1 upon k, where k is a very important constant that we call as dielectric constant. It is an inherent property of this dielectric. So it is dielectric constant of the dielectric. This is also called as relative permittivity. It is also called as relative permittivity of the dielectric. Is it clear, students? So let's see what our E becomes. So this E now can be written like this. E is equal to this means this one, sigma minus sigma p. So I can write sigma minus sigma p is how much? Sigma upon k. This sigma minus sigma p I have written as sigma upon k, and this epsilon naught will be there like so. Now what is our sigma by epsilon naught? That is equal to E naught. So sigma by epsilon naught was E naught. So our E becomes E naught upon k. Now this is what you have to remember. If you have two oppositely charged conducting plates with vacuum in between the plates, then the electric field between them is given by the formula E naught is equal to sigma by epsilon naught. Okay, but if in this space you fill some dielectric of dielectric constant k, then the electric field gets modified, and the new electric field E will become how much? E naught upon k, or that can be written as sigma upon epsilon naught times k. It is this which you should remember as the gist of this particular discussion. In absence of dielectric, it is E naught, that is sigma by epsilon naught, and if you put a dielectric that fills completely the space between them, then inside the dielectric the net electric field will be E naught minus E in, and that on solving we find it to be how much? Original electric field divided by k. And needless to say, students, this value of k is always greater than 1. K is greater than 1 means E should be less than E naught. So the electric field inside the dielectric gets reduced by a factor of k. What is k? K is the dielectric constant or relative permittivity. So let us quickly discuss what happens to the capacitance in case of a capacitor, wherein in between the plates we have inserted some dielectric. So suppose we have a capacitor like this having surface charge densities plus sigma and minus sigma, and there is vacuum. Then in between them we know that there will be electric field E naught. E naught will be how much? Sigma upon epsilon naught. And we have discussed V. Suppose this plate is A, this plate is B, suppose. Then V will become how much? VA minus VB, and that we have solved it to be how much? E times this separation between the plates, E times D. And this we have calculated. E is sigma by epsilon naught. Sigma we can write as Q upon A. That on solving we get C is equal to how much? A epsilon naught upon D. This is the situation when there is vacuum between the plates or air between the plates of the capacitor. Now suppose we insert some dielectric. Here we insert a dielectric of dielectric constant how much? K. then what modification we will get? First, the electric field will get modified. E inside the region between the plates will now no longer remain E naught. It becomes E naught minus E in. That E in depends upon the polarized charges. And on solving, we find it becomes E is equal to E naught by K. If E becomes E naught by K, E naught is how much? Sigma upon epsilon naught. So here we'll have sigma by epsilon naught times K, and sigma is Q upon A. So we have this much. And likewise V, the potential difference between the two plates, which is V A minus VB, will become equal to the net electric field E times D. So which will become how much? Q upon A epsilon naught K upon D. And now the new capacitance C, which is equal to Q upon V. So Q upon V will become how much? A epsilon naught K upon D. So this was the capacitance in vacuum, A epsilon naught upon D, and this is the capacitance in presence of a medium. That medium has a dielectric constant K. So we find that the capacitance is K times the original capacitance, and we had discussed K is greater than 1, and therefore we can write C is greater than C naught. Remember, E is less than E naught. E decreases by a factor of K. Capacitance increases by a factor of K. So you can find numericals based on simple numericals based on these capacitance of parallel plate capacitor with or without dielectrics. Some of them you will find in the assignment, students. Please do them. In the next class, we will proceed to some more questions wherein only a little space between the plates of the capacitor will be filled with dielectric. We will see such different combinations, and they will be important for your board exams. So for now, I'll stop here. Please read this topic carefully, and in the next class, this was just introduction on capacitors, and next class we will do some problems on capacitances. So thank you. See you in the next class.